What's up, scholars? Today we're going to be introducing some concepts in rotational dynamics, namely rotational inertia. Before we jump into that, I want to remind you, so we're going to recall that each linear quantity we talked about so far, especially earlier on in the semester, has an analog to a rotational quantity. So for example, linear velocity, which we typically use the letter v for, its angular equivalent or analog is angular velocity. Remember, we used the symbol omega for that. So in this unit 8.3, where we're going to be looking at things moving in a circle and they're going to be dynamically doing that. So they're going to be accelerating, slowing down, speeding up, etc. To do that, we need to look at the following thing. So in addition to, velocity, position, acceleration, and so on, the specific things that we want to look at are as follows. We've got mass, force, kinetic energy, and momentum. Again, each of those has a rotational, or sometimes we might say angular version of it. The angular version of mass is something called the moment of inertia, which we've talked about a little bit before. We used the symbol I for that. We used, remember, little m for mass. For force, remember, we used the letter F. The analog to that is, of course, torque, which we've been talking quite a bit about. We've got kinetic energy. Now I want to amend this a little bit, which is to say that this kinetic energy is the linear version, or we might sometimes call that the translational. Translational. As we've discussed, remember, translational means moving in a straight line, so maybe for now let's call that Ke with a little subscript t. Not surprisingly, if things move around in a circle, the analog is going to be called rotational kinetic energy. So rotational kinetic energy. And we'll just, for right now, go with Ke with a little subscript r, meaning rotational. And then finally, we had momentum, which, if you recall, we used the letter lowercase p. In this new world, we've got with something that we like to call angular momentum. So angular momentum, we use the capital letter L to represent. So in this video, we're going to be mainly talking about the moment of inertia, and I want to give you a helpful hint before we jump in, which is when you're trying to solve rotational or angular problems, which we're going to be doing here, the easiest way to wrap your mind around it, especially since this is so new, is to try to think of the linear version of that problem. So for example, you can compare the two velocity ideas, concepts. So we've got linear velocity, which most of us are familiar with from driving or just generally watching things move around. Most of us can remember off the top of our heads that linear velocity is distance over time. Think miles per hour in a car. So we can get that pretty easily. Now the analog is just throw angular or rotational in front of like the measured quantities like distance. So this would just be like the angular distance over time. So instead of linear velocity being something like how fast is something moving in a straight line, angular velocity is how fast is something moving in a circle. The first thing I want to directly compare is mass and the moment of inertia. So let's quickly remind ourselves of what mass means. Think about the difference between a mouse and an elephant. So, pardon the sloppy drawing, but we've got something very, very small, maybe a few hundred grams like a mouse, compared to something like an elephant, which can be many thousand kilograms in terms of mass. So what is mass? Mass is something's resistance to being accelerated. In other words, if we applied the same amount of force to an elephant and a mouse, obviously the mouse would accelerate more. In fact, if we take Newton's second law and solve it for acceleration, we can see how that works. So if you have a big M on the bottom with the same force, your acceleration is quite small. This is our first exercise in thinking about, okay, how do we take something mass, which is a linear quantity, and think about it in terms of rotation. Let's take our little trick from earlier and just add the word angular in. So whereas mass is the tendency to resist acceleration, let's just say for now, and this is actually a pretty good way to think about it, the moment of inertia of an object is its tendency to resist angular acceleration. Let's try to switch views here. And I tried to put together a way to demonstrate what moment of inertia is. So I've got these two cans taped to this meter stick. They're full, and I've got them about 15 centimeters from the middle. So if I pick this up at the middle and I rotate it, it's pretty easy to rotate this, and we'll see why in a moment. That's because the distance to the cans is relatively small. It turns out that the farther away I make the cans, the more difficult it is to rotate it. I'll show you that now. So now I've significantly increased the distance that they are away. I've doubled, actually, the distance that they are away. And it is much more difficult to rotate this thing because I've increased the distance. So by doing that, and we'll look at the details of the equation for why I would increase it, but I've made it harder to rotate, so I've increased its moment of inertia. Now, importantly, I didn't do anything to the mass. There's still the same two cans. It's still the same meter stick. What I've done is I've moved it farther away, and we'll see why in the equation it makes it harder to rotate it, or it increases the moment of inertia by moving the mass farther away. So let's jot that down on our paper. Oh, it's not working. I'm hoping you're going to be able to see this, but part of the classic example of talking about moment of inertia is looking at ice skaters. They're one of the most classic examples of it. If you watch this ice skater here, they're actually, apparently according to this GIF, setting a world record. What they're doing is they're pulling their arms and legs in, which decreases their moment of inertia. We'll look at details on that later. They're pulling the mass of their arms and legs in closer to the center, and that means that they're decreasing their moment of inertia, which means that it's easier for them to do angular acceleration. It's easier for them to spin around. So that is another case where this is a really important concept. So we're going to look at a couple of different versions of equations for the moment of inertia. There's sort of like the math brute force way to calculate the moment of inertia, which I'd like to show you now. Moment of inertia, it turns out, it depends on the sum of how heavy each thing is in a system that's rotating, the mass, times its distance from the rotation point squared. So I don't know how well you're going to be able to see this, but if we go back to my funny cans on the meter stick situation, what we would have is we would need to know the mass of each of those, and we'll do this in a moment, and the distance from the 50 centimeter mark right here in the middle. And so for each object, maybe we could have more of these cans on there. For each object, you simply add its mass and distance squared away from the center point. That is the mathematical way to calculate the moment of inertia. So we'll call that equation 1 for moment of inertia. Now the second equation, I've kind of already hinted at it here, is going to come from a little bit more of a direct measurement of some familiar quantities. So if we look at the linear case of mass, we have F equals ma, the standard Newton's second law, and if we rearrange that for mass, you can actually calculate the mass of something in this manner. If you know how much force is being exerted on it, and you can somehow measure its acceleration, you can pretty easily get at its mass. If we think of Newton's second law, but for rotation, that's torque is equal to, instead of mass, it's the moment of inertia, and instead of linear acceleration, it's going to be angular acceleration. So we can call this the second equation for the moment of inertia. It would just be directly measuring the torque and angular acceleration, and that would give us the moment of inertia. I made a tiny modification. To be clear, these should be net force and net torque if we're going to use that method. And I've also put boxes around those two important ways we can look at moment of inertia. Now, to be clear, if moment of inertia shows up in any equation, if you measure all the other quantities, of course, you can get at it. So what we're going to do next is we're going to make a quick calculation using each of the two equations. We will sort of brute force our way to calculating the moment of inertia of the example I gave you earlier with the ruler in the cans, and then I'll give you an example here with something having a torque applied to it and us measuring its acceleration. But before we do that, I want to show you that in general, we're not going to be calculating moments of inertia all that often. And the reason for that is because if you don't have anything that's very simple, like what I just showed you there with masses at specific distances away. For example, these different kinds of shapes. These shapes here are pretty standard versions of common moments of inertia, as you can see here. So you're going to notice a few things. Each one is going to have an mr squared. So here you've got a solid disk, here you've got a hoop, and so on. Each one is essentially some constant out in front. So 1/2, 2/5, 1/12, depending on its geometry. You can even see, for example, the difference between rotating a hoop from its center versus spinning it through its center, or a rod spinning about its center versus a rod spinning about the end. But each one has just a constant out in front times m times the distance squared, and so you'll use this if you ever don't know the moment of inertia. Often it will be told to you, though. I'd like to show you a couple of examples. Let's go back to the one I mentioned with the cans. So the 2 cans, each of mass 1/2 kilogram, are secured to a meter stick. Let's just say the meter stick is negligible for right now in terms of mass. We're going to find the moment of inertia of the system in 2 different situations. So the first, where I had taped it 0.15 meters from the center, and then the second, where I doubled that distance to 0.30, 30 centimeters away from the center. So I've done a bit of setting up. I've drawn both situations. I've reminded ourselves of the equation. So remember, a moment of inertia is just add up each object with its mass and distance squared, and that ends up giving you the moment of inertia. So I've got both of them set up here. I've just used subscripts to represent this mass and its distance, this mass and its distance, and so on. So this calculation is really great because it's going to show us both the units and sort of how moment of inertia works. So for the one on the left, I've plugged everything in. You get 0.0225. We'll figure out the units in just a second. And for the other one, where I doubled the distance, we end up with 4 times that amount, 0.090. Just to verify that it is indeed 4 times larger, I just did a quick division there. Those numbers aren't very intuitive. So you can see how this worked. I doubled the distance of the masses, and it quadrupled the moment of inertia. The last thing I want to do on this example is figure out the units. So if we look carefully, both of them have kilograms, and then you've got meters, and it's going to get squared, and that term is the same. They're just being added together. So this is going to be kilograms meters squared. Likewise for this one. So there are our 2 sort of moments of inertia. So as I showed earlier in this set of video notes, when I moved the masses out farther, it was harder to rotate them. Or we should say that it tends to resist angular acceleration more easily. So to take this full circle, if we take this rotational example and go back to linear, that's like taking a 1 kilogram mass and a 4 kilogram mass and comparing how hard it is to throw them or how hard it is to accelerate them. Alright, so a second example, we're going to use the other version, the other way we can determine something's moment of inertia. So it says a child pushes their friend on a merry-go-round by exerting a torque of 250 Newton meters. The merry-go-round starts from rest and reaches an angular speed of 5.0 radians per second in a time of 10 seconds. What is the moment of inertia of the merry-go-round child system? So probably a pretty familiar playground situation. This person on the edge here exerting a torque, this person going round and round on the merry-go-round. A couple details we were told is that this takes 10 seconds to get them up to their final rotational velocity or rotational speed of 5.0 radians per second, and we're going to simply use the moment of inertia is going to be equal to the net torque divided by the angular acceleration equation we developed a moment ago. In this fairly simple example, we are going to need to know the angular acceleration. Got to be careful there. The angular acceleration, which can be defined as the final angular velocity minus the initial divided by the time. Remember, if you're not sure, you can always go back. What is linear acceleration? Linear acceleration is the change in velocity over time, v final minus v initial. So there's our analog showing up again, helping us out. let's pop in the numbers and calculate the angular acceleration. I might try to make the numbers nice and easy. We end up with 0.5. That's radians per second squared for the angular acceleration. Now we can pretty easily calculate the moment of inertia. We are already told the net torque on our rotating system is 250 Newton meters. We're just going to divide that by 0.5 radians per second squared, and you get 500 for our moment of inertia. Remember from just a moment ago, from the definition, we ended up getting kilograms meters squared is our unit, so we'll use that here. It's not quite so obvious that that should be the unit. If you break down what newtons are, you do end up with kilograms meters squared. So you likely at this time won't have an intuitive sense for like what's a big number, what's a small number for moment of inertia, but that's okay. So folks, there you have it. The two different ways that we can get at the moment of inertia of an object. We can calculate it by knowing all the masses and distances, or we can know the torque and know the acceleration and find it that way. Thank you so much.